Hello. In this video we will implement vector-vector addition on FPGA using Protoip software tool. The algorithm of interest is the following. We have two input vectors, 10 elements each, x1 and x2, and one output vector of the same dimension. And what we're trying to implement is add x1 plus x2 in order to get y. Okay. The design flow with FPGA with Protoip software tool is the following. Firstly, we will create a template. For this particular tutorial, we will use PLT programmable logic template. Then, once the template is created, we will modify the template code in order to implement our algorithm. After that, we will perform HLS, high-level synthesis. In other words, we will transform high-level C or C++ code into lower-level HDL, hardware description language code. This will be done using IP design build function within Protoip. Once HDL code is obtained, we call IP prototype build function in order to transform this HDL code into the actual circuit. So once we get a bit stream that describes our circuit, we upload this bit stream to evaluation board and test the algorithm in hardware in the loop test. So now let us come to practice. In this tutorial we will use MATLAB interface. I have a script with a set of commands, and we will uncomment them one by one in order to go through all the steps of the design flow. So the first command is make template. So make template command has a set of arguments. So firstly, we define the type of template. In this case we use PL template. Then we choose a certain name of our project 0. And the last thing we have to define is the set of interface vectors. So for our example, we have two input vectors, x1 and x2, and one output vector y. So we have 10 elements in each interface, and we choose floating point implementation for all the interfaces. Now I run this command. Okay, the template is created, and now let's see if Protoip did its job. So we come back to the folder with the script. So test M is our script with a set of commands, and we can see that Protoip generated a set of folders with template files. So firstly we go to doc folder. In this folder we have a text file that describes all the interfaces that were created. So we have x1 vector, 10 elements, x2, and the output vector y. Okay, we can find some additional information as well, but we will not go through it in this tutorial. Okay, apart from doc folder, we have IP design and IP prototype folders. IP design contains Vivado HLS project and some source files. So we go to IP design and then to SRC, and we will see a set of files, and some of these files will be modified by users. So we will modify some of these files. Before we do this, we have a look on the last folder, IP prototype. So IP prototype is a Vivado project, and it incorporates the whole block design of the entire Zinc SoC. Okay, our goal is to implement vector-vector addition this one. And in order to do this, we have to modify one of the generated C files in such a way that the algorithm will do what we want. So we go to IP design, then to SRC, and our goal is to modify foo user function. Uh, okay, so foo user, so Protoip provides a template, but we will not use it for our purposes because we have our own algorithm. So we have a function with three arguments. So we have three pointers to three arrays, and we will implement element-wise addition. We'll create a counter and then a for loop that will perform element-wise addition. So we know that the sizes of these arrays are the same, and our goal is to add them. Okay, now this seems to be correct, and we can go ahead and synthesize the code. We go back to MATLAB environment. We don't need make template command anymore. We can go and call IP design build function. Make sure that the project name is the same with make template. Okay, and we call IP design build. Okay, it seems that IP design build finished execution, and we get a report from Vivado HLS that IP is built successfully, and Protoip automatically provides resource usage information and loads it to the MATLAB workspace. So here we can see that resource usage values for different resources types is uploaded to the workspace for BRAM, DSP, flip-flops, lookup tables, and also we get a latency estimation of our algorithm and some other values, and the details on this are available on Protoip wiki on GitHub. Once the IP design build function finishes execution, this means that we have an HDL code. We are on this stage right now. We have HDL code, and our goal is to convert this HDL code into FPGA circuit bitstream, and we do this by calling IP prototype build command. We come back to MATLAB environment, and we call IP prototype build command, and at this stage we have to specify the project name as we previously did, and also we have to specify the board that we use. So in this for this example we use the Z board, and we provide this information to this function. So now I call this function, I call Protoip IP prototype build function. As we see, IP prototype build function has finished execution, and we can see a report saying that FPGA prototype is built successfully. At the moment, we are on this stage of the design flow. We have FPGA circuit bitstream that is supposed to be uploaded to the actual hardware, and it is the right time to check all the interfaces on our board, including USB, Ethernet, and it is also important to make sure that there is a power supply on our board. In order to upload FPGA circuit bitstream onto the evaluation board, we will call IP prototype load function. I will go back to MATLAB command line environment and I call IP prototype load. Okay, now IP prototype load command has finished execution, and we can see the report saying that FPGA prototype is ready to be used. And now we'll come back to the design flow. So what we have reached at the moment is we have loaded prototype on the evaluation board, and the last stage of the design flow is to test this prototype. To do this, we will use IP prototype test function, this one. So this function has three arguments: project name, board name, and the number of tests. So for this particular algorithm, one test is enough. And now everything is ready to perform the test. Okay, the test is finished, and now we will go back to the Protoip folder to see the results of that test. So I go to the folder with the project, and I go to the IP prototype test results, and we have only one project. Okay, and for this project we have 5 files with the test results. So I will start from the bottom. We have two text files with two input vectors, so x1 and x2. So we have x1 and x2. So these files contain input data that was randomly generated by Protoip. So we have 10 elements in each file. Okay, these are input values, and we want to see what are the output values. We go to FPGA yout log.dat. Okay, and in this file we have the result of our algorithm execution. So in order to verify the correctness, we take the first element from this from the first vector, which is 4 point something minus 1.71, and we get 2.43, which seems to be correct. The same thing can be done for all other elements, but we will not do this in this tutorial. And the last thing we want to check is execution time. I go to FPGA time log, and here I see two numbers. The first number is the time that our algorithm required for the execution. In other words, this is the latency of our algorithm in seconds. And the second value is the communication time, so time it took to exchange data between FPGA and desktop machine. To make the structure of this hardware in the loop test clearer, we will consider this diagram, which is a kind of summary of this tutorial. So in the beginning we created a template, and by calling make template command we have generated a set of files. So we had some files in IP design folder, IP prototype, and another set of files in IP design folder. Okay, we generated these files, and the second stage of the design flow was modifying fooUser.cpp file. So we have modified this file, and then we called IP prototype build command in order to build this Vivado HLS project. Then we called IP prototype build command, which incorporated the whole system on a chip It incorporates Vivado HLS command, Xilinx SDK, and Vivado itself uh, in order to build system on a chip. Note that with programmable logic template that we are using now, user's code does not go to CPU. So for CPU we have a set of files that manage data transfer between personal computer and FPGA. And on the computer side we have three files on this diagram, and the most important one I think is testhill.m. And by modifying this file we can change our test conditions. So if we go to this file ipdesign src test hill, okay, test hill, this is a MATLAB file, and we can observe that the input data was generated in a random way. So this is the input data for x1 and this is input data for x2, and user can change these lines according to his needs. So if user wants to check his algorithm under different conditions, he might want to change these lines in order to change the behavior of the hill test. Okay, that's all about hardware in the loop test. And the last point in this tutorial will be IP design build debug command. So we went through a set of commands, and it is important to keep in mind that each of these commands, apart from make template, has a debug mode. In debug mode, we can actually open the underlying project. By project I mean Vivado project, Vivado HLS, Xilinx SDK project, in order to manually make changes. So once we learn new things about FPGAs, if we want to take control over some low-level implementation details, we can call corresponding debug command and change the project settings manually. I will show the example just for IP design build command. So we called IP design build command in the beginning, and now I will call IP design build debug, which has the same set of arguments as IP design build itself. So I call this command, and Protoip opens Vivado project that can be changed manually. So what we will do, we will go through the set of source files. So we have a set of source files, and this file foo_user.cpp that we modified. So here it is, and we see that we can change it here, and we can perform synthesis manually, and this allows us taking control over low-level details. And the most important thing is that this allows us applying directives. So we have a for loop. If we put a label on it, let's say main loop, I save the file, and we can see this main loop on the right hand side, and we can insert directives. Let's say I want to pipeline this loop. I would add this directive to the source file. Okay, so I put this pragma. So low-level things like this can be implemented directly using Vivado HLS project, and once this tuning is finished, we close the project. Protoip will automatically detect and save all the changes, and after we finish debug, we execute IP design build again, and we can go through all the steps of the design flow as we previously did. It is important to remember that these debug versions of Protoip commands are available for for other commands as well. And to learn more about this, please refer to the Protoip wiki on GitHub. Thanks for listening.